Okay, so welcome everyone. Today's speaker is Kalpesh Garg, and he's a fifth year graduate student at the University of Mumbai, and he's currently visiting HAO as a graduate Newkirk Fellow. And his research background is in solar terrestrial physics with a focus on the impacts of solar wind transients, such as interplanetary coronal mass ejections, high-speed solar wind streams, and solar energetic particles on space weather. And in July 2024, he began visiting HAO under the Newkirk Fellowship, where he's been working on MIT coupling studies with Bill Lotko, Kevin Pham, and Mike Wiltberger. And his focus is to simulate and diagnose storms and other events using MAGE. And so today he will give presentation on the universal time influence on storm time, magnetosphere, ionosphere coupling. Go ahead.
Yeah, thanks, Nick. As Nick mentioned, to clarify that, means I came here last year. Until that, my background was in solar wind physics, specifically focus on interplanetary counterpart of coronal mass ejection and its dynamic with geomagnetic storm and everything associated with ICMEs. But since I came here last July, and to be told, I came here to do something like uh, some solar wind correction in IMF BX. I worked for a few months, but later we focus on this particular topic that I'm presenting here. Thanks for all my collaborators, Bill, Kevin, Don, Slava, my advisor from university, and Mike. So when we talk about solar wind, magnetosphere, ionosphere coupling, that the first thing that we need to mention about the magnetic reconnection and the energy cycle that we need to acknowledge as here this particular animation specifically with or developed by a specific this institute, NCAR, you see that a southward component of the magnetic field is coming from the left and it's reconnecting at the magnetopoles. Then that solar wind magnetic field get dragged at the night side, and again there is night side reconnection, which again comes that magnetic field lines at the day side through dawn or dusk. Here it's shown only through the either side, but it comes from both side. And if we look at the left figure or the left animation where you specifically are looking from the North Pole and there is the convection pattern. When the things are happening in a magnetosphere or in the solar wind, the reconnection, then the dragging of magnetic field line at the night side, and again, and the night side reconnection. So the magnetic field lines are being enrooted in the ionosphere, and the things that being reflected here in ionosphere, as you see the plasma which moves known to be as a convection cell. And whatever I talked in that in animation, this is somewhat like a textbook understanding of that, like a solar wind magnetic field, a bow shock, a various region from the magnetosphere. And you see here on the left side, a top of left, where it's specifically a polar region, a polar cap, then a gray shaded oval specifically. You see the convection cells here. And with connection to that, we have the different current systems. And the important is like field line current system, where you see the both region 1 and the region 2 currents are there, and the red color specifically showing the upward field line current means the electrons going down, blue color showing the downward field line current where the electrons are coming out. The inner current or inertia is known to be at R1, region 1, then the outer called as a region 2. So all the systems is coupled, and that we know. The as this topic is more focused on the UT variation or UT influence, I need to introduce some fact about it. So when we when we as we know about our rotation axis being tilted by 23 degree, and our magnetic axis is also tilted as corresponding to that rotational axis by 11 degree, we have the kite offset between the two axes, that is the rotational and the magnetic axis. And as Earth rotates, these magnetic axis rotates around the rotational axis, or we can say wobbles around the rotation axis. And a kind of metric that we measure how that dipole tilt and how it varies is like a dipole tilt angle that is shown here by the delta. And that dipole tilt angle varies as Earth rotates. It varies from -34 to +34, and it depends on the season as well. So as we know, this particular dipole tilt as a function of UT, and that's been a UT variation that we are going to look forward. So when we talk about that particular poleward motion, as the pole moves towards sun or towards anti-sunward, you can see the respective change in a magnetosphere here. It's a schematic diagram. So if you see here at 5 UT, when the pole or the north pole is quite anti-sunward, or and the other side there, at 11 UT, it's quite aligned. Then at 17 UT, it's quite tilted towards the sun. And again, so in 24 hours, it's been going sunward, anti-sunward kind of thing. And that creates some kind of dynamics over there. So it creates like it changes where the reconnection occurs and all these things. So this being focused on only for the magnetosphere. And when we go for the ionosphere, we know about the potential. We introduce the field line current, but there is one another factor that controls or that regulates this potential and all is the conductivity. And if you see the equation, uh, specifically here on the right of top, it's a basic coupling equation where the input is field line current, that is J parallel, and with the given conductivity we can solve this equation to find out the potentials that the equipotential counters on the ionospheric surface. And as we know, or as this specifically, the potential or this counter being controlled by the conductivity, and this conductivity is specifically dominated or specifically just the conductivity is or the conductivity drives the current. And there are typically two type of currents, like Pedersen current and the Hall current. And the Pedersen currents are like at as the electric field come down, is generally the ions which first demagnetize from the magnetic field and they move with the electric field, and that's the Pedersen current. And as the electrons which are still attached to the magnetic field, and due to their higher gyro frequency and higher less or the small gyro radii, they experience a drift, that is E cross B drift, and they move towards both perpendicular to the direction of E and B, and that's the Hall current. So these two currents are there in ionosphere, and the specific conductivities, that is sigma P, that is Pedersen conductivity, and the Hall conductivity, they controls this current. And both these Hall conductivity and the Pedersen conductivity, they are dominated by EUV ionization, solar illumination at the day side, and at specifically at the night side, they are dominated by the impact ionization or the particle precipitation is a whole there, but they are dominated by it. So as specifically, this figure means, as I mentioned, these conductivities, they are being dominated by the EUV illumination, and as pole moves towards or sunward or anti-sunward towards anti-sunward, the conductivity also varies. So if you see a figure here, it shows annual or a diagonal variation of specifically sigma p. This is figured by, this is from Ridley 2004 et al. Specifically model. And if you see here, let's talk about this figure, and let's forget about what's there on the y-axis. Let's focus on the x-axis. So here, x-axis, it's a fraction of year. This means that if this is for the whole year. So fraction of year means each month. So if you go here for the 0.5, this means this is at 30th June. So for the whole year, and the color is denoting the sigma p, that is a Pedersen conductivity. And if you see here specifically at means if we focus specifically on the north polar cap first, you see here the high conductivity, which is at around 0.5, means around June. And this shows here, if you see on the left plot, which shows that at June specifically, the northern pole is much toward the sun. So that's why we see the enhanced conductivity there in the north polar cap for the fraction of 0.5. This is on the second column, specifically for the north day oval, and the third column is for the night oval. And you see it's varies, like for annual variation for north polar cap, it's been more concentrated at 0.5, means related to a June solstice. And when we look at the south polar cap specifically, you see here they both are being dominated here at 0 and 1, means this means that at south pole there's the higher conductivity is there at the December solstice. So as the south pole being more tilted towards the sun, so that's why we see this kind of variation. And more, if you see on the y-axis, it's a UT variation, that is a diagonal variation. The variation that we saw here is, sorry, the variation that we saw here, it's annual variation or the seasonal variation, we can say. But here the variation is UT when the pole move or toward the sun or pole move anti-sunward. The variation is there across the conductivity as the solar illumination is being affected there. And that's why it's a UT variation. So when we talk about UT variation, it's almost obvious for ionosphere, thermosphere people, because they know about the solar illumination. Things are quite being changing over the UT or the daytime. But specifically when I talk to the magnetosphere people, it's quite been like a curiosity. How means we know the ionospheric things, like how they change for the conductance and all these things changes with the day or day night. But for the magnetosphere people, it's still a question, like, does the universal time of storm onset specifically influence geospace consequence? Or we can, in simple word, is it matters at what time or at what specific UT the storm hits our magnetosphere, and the storm evolution is being dependent on this universal time variation? That's been our specific question. And for that we use MAGE, that is multi-scale atmosphere geospace environmental simulation, and led by Center for Geospace Storm. And as we might aware of all this model, like the specific module or the framework that we use for this work is MAGE 1.0, a MAGE 0.0 or 1.0 and MAGE 0.75 or 0.75. The MAGE 0.75 generally consists of a Gamera, which is MHD solver, and then the remix, which is a ionospheric solver, which solves that coupled equation, and RCM, which is ring current or Rice convection model, or the inner magnetosphere model. And when we go for MAGE 1.0, it consists of the Tigesium ionosphere thermosphere, a physics-based ionosphere thermosphere model, where the remix is quite empirical. And along with that, we have precipitation in the MAGE, as there are basically three type of precipitation. If we see monoenergetic precipitation, diffuse precipitation, I'm talking about electron precipitation, and broadband precipitation. So the main monoenergetic precipitation is like when particle comes parallel to the magnetic field line, the quasi-static potential gap being developed there, and with that electric field, the particle being accelerated and they comes towards downside. And the diffuse precipitation is somewhat like with the due to the pitch angle scattering and the mirror point of the particular particles when it comes near the ionosphere. So particle will precipitate come in the ionosphere region. And when we talked about the broadband precipitation, it's quite a low or comparatively low energetic particles being as compared to mono and diffuse. With these particles are being being propagated by dispersive alphanic waves. So this model has both monoenergetic and diffuse precipitation, and my intention to introduce it here because we are performing few kind of experiments there with this monoenergetic precipitation and diffuse precipitation, so we can get an idea about it. So this is about the October storm. On 10th October 2024, CME hits our magnetosphere or Earth. And if you see, the CME is quite, means we see that this CME is quite, generally in interplanetary space, these CME, they no more propagate or no more comes like alone inside in solar wind. They always have, like, sometimes they have interact with other ICMEs, sometimes it interacts with other solar wind. But this ICME is, it seems to be an isolated, nice sheath region specifically. Means if we talked about ICME, there are substructure like ICME sheath and ICME magnetic cloud, a magnetic cloud where the flux of structure is there. And you see here a shock region, and then there is a sheath where the magnetic field is fluctuating, kind of turbulent. And then when we go for magnetic cloud, the magnetic field variation are like there are smooth variation in a magnetic field, and that's the criteria to differentiate sheath and cloud. And if you see here, the high dynamic pressure, initially number density increase there. Oh, sorry, the dynamic pressure is increased there, then the velocity profile. And on the left side, these are specifically the photographs of auroras taken during this particular storm. So I think the leftmost is one of the friend is there in UCL, University College London at UK, and she took this photograph at 22 BST at night, and which is associated with 21 UT. So if you see here, this substorm was there. And when I took these photographs on specifically at South Boulder, Table Mesa, the time here is around 20 Mountain Denver time. And if you see here, this associated with this substorm. And the feature about this storm is like it has a sudden storm commencement, SSC initial phase, and then it's a main phase, and then it's a recovery phase. So if we go for the whole time for the storm, it lasted for 1.5 days. And if you see specifically here in this main phase, there is a small dip, and the storm main phase is extended here. The storm peaks at specifically this point, at I think at 2 UT on 11th of October. But this is quite a deep associated with that, and with this associated in this C match, and we are not identified any kind of the driver of this particular dip in solar wind or in interplanetary parameter. So we are still thinking about this, and we are still looking forward for this. What's the cause, and what's the cause that sudden dip? But it is associated with some transient phenomena. This is storm's time magnetosphere. If you see, on the left, it is simulated residual magnetic field, that is B simulated minus B dipole. On the right, it's thermal pressure in X Z plane. The left side is in Y or X plane, and there are field line currents here, and if you see how the shock is coming, how it's changing, the magnetopause is being, means if we see initially it being here at around or somewhat around 7 8 9, then when it comes, it goes inside specifically. So this is about the storm time magnetosphere. The 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 important aspect about this particular storm that we observed is, if you look at right side figure specifically, and the first row, which is a first figure, is about the field aligned currents from remix, distribution of field aligned current. The middle At middle, it is a Pedersen conductivity, so Pedersen conductance, and at last, it's Hall conductance. The first row is for north hemisphere. The second row for the south hemisphere. And if you see here specifically in Pedersen conductivity, you can observe that at north, the conductivity here at the day side is quite around 7, or we can say 7 to 10, but at south it's around 11 to 7.5. You see the precipitation and the current patterns are there. They are also different in both hemisphere. And if we plot the integrated parameters for or with the time series, and we observe that there is a difference in the parameters from north to south. If you see here on the left side, the first panel shows the CPCP, that is potential, cross polar cap potential. And you see the potentials are dominated here, that specific region in the northern hemisphere, than the southern hemisphere. For FACs, that is field aligned current, integrated field aligned current, you see here it is dominated at southern hemisphere than northern. Then EHP, that is hemispheric power through electron or particle precipitation. You see here it is also dominated in the south than the north, and which is a Joule heating being derived from the Pedersen conductivity. You see here that also dominated at south, so which is significant interhemispheric asymmetry that we observe. This specifically is from the GR, that is using MAGE 0.75, and where the conductance or the potentials or the remix is, or the conductance is empirical. But when we go for a GTR, where TiGCM comes in the picture, we are observing a similar kind of things, but the things are quite different here due to a physics-based conductance model due to TiGCM. So you see, same, like we observed the interhemispheric asymmetry here, but if you see the potentials or at the south in GTR run, so they being lower here, and if you see here, it is around or the more than 300, and here they are less almost or it is around 300 or less than 300, and it is specifically due to the increase in conductance in the south hemisphere, that why potential being reduced. You see that the difference is quite there. Quantitatively it is different, but the qualitatively what we are observing in a GR, we are similar kind of trend we are observing in a GTR. So the interhemispheric asymmetry, and this storm is specifically at October or near to the equinox. So that was a surprise for us, like near equinox storm. How we can expect this kind of interhemispheric asymmetries? So then we go for some controlled experiment. That means, with the previous literature we know that there are few factors that affect the interhemispheric asymmetry, and then with made or the simulation gives us that liberty to either shut down typical of some factor or that kind of experiment. So for that, we did few controlled simulation, and as we know, there are specific factor that affects the interhemispheric asymmetries. That is IMF BY. There is one person sitting in this room. He's been more focused for this interhemispheric asymmetry, and he's giving colloquium next week. So Jonas, so with that, we know that the BY is specifically one of the uh, factor in interhemispheric asymmetry. And if we look at the solar wind or the interplanetary parameter for the storm, you see that the BY is quite been means at around more than 20 nanotesla here. The BZ is elevated, like it's almost 40 nanotesla, but the BY is also there, which is around 20 nanotesla. So we thought that it might be a reason, and so we did a simulation with minimizing the effect of BY. We cannot make the BY zero, because at certain point it will create the whole IMF as a zero and will cause error. So we keep BY is equal to 1, but we didn't see any kind of changes here. Yeah, with quantitatively there is some modulation, but the asymmetry for that particular region is still there. Then we thought we should change the orientation of BY. So we inverted the BY, like changing the sign of BY. So we were expecting that changing the BY will change the direction of asymmetry, but it also didn't have any effect over it. If you see both of this is with original and this is with controlled simulation or controlled run. So you see still there, since the asymmetry is still there. So as I explained, there are the precipitation, like we have the precipitation like monoenergetic precipitation and diffuse precipitation. So and if you see here in this particular plot, where the monoenergetic precipitation is associated with a field aligned current, which is upward because the electrons are going down. So they are dominated, if you see, at the dusk side. So the dusk side region, if you see on the north pole, the precipitation, the conductivity due to the precipitation is like, yeah, moderate, but in south you see it is being enhanced. So we thought that the monoenergetic precipitation kind of thing might be one of the contributing factor in this asymmetry. So we did simulation to without monoenergetic precipitation, allowing only diffuse, and for that still we observed a symmetric nature for hemispheric power through the particle precipitation, but the asymmetry in potential or in current is still there. So next we went for like keeping EUV constant, Pedersen conductivity constant at both hemisphere. And then we observe that the everything is quite symmetric. So the asymmetry is reduced, and the storm which is near equinox, still the EUV conductance, the conductance with EUV is one of the major factor. But how? The thing that
That's good. Yeah. So this is from a GTR or from a
GR, GR. We are
okay.
doing everything for the GR because it's quite easy to
Okay. Okay.
do the controls.
Okay.
Yeah. So the thing that we acknowledge uh, at initially about the offset of the magnetic axis and the rotational axis. So here, if you see, we plotted the dipole tilt, that is delta, with these parameters. Like first, it is IMF BZ, then it is dipole tilt, then the CPCP from GR1, then the difference between the CPCP, that is north minus south, and the CMAC. So there is quite a coincidence here when you see here the dipole tilt, which is being positive, and it is going at a negative. Means a positive dipole tilt means a dipole like it is oriented or it is close to this perpendicular axis, and it is going negative. And it is going negative. This means that the north pole is going backward and the south pole was just turning towards the sun. So the step in that particular BZ occurred at the same time, such as when the south pole was more turning toward the sun, the BZ flipped and it went for the storm peak. And during that time, if you see, we observe the asymmetry. And when the dipole tilt, which is again coming toward a normal, where again the south pole is coming at anti-sunward, you see the asymmetry being vanished. So we did another run where we shifted the UT of the particular storm. The UT shifted means we shifted the tilt. So by 12 hours, so if you see here at particularly this, it is like a dip. Here it's increase in that dipole tilt. So you observe that when we shifted the storm by 12 hours, you see the asymmetry is also shifted by the 12 hours. So for the better comparison, we have kept the time for the both of the runs similar, but here it is a UT shifted. You observe that the storm, when it is shifted by 12 hours ahead, you see the asymmetry being shifted at initial time. And here it's also, and the region where we are observing the asymmetry in a previous run, which is now a more symmetric. So this is somewhat, oh yeah, long.
Yeah, hey Kapash, just to make sure I understand it correctly. So when you do that UT shift, did you only shift the UT in the dipole tilt time series?
Yeah.
Okay,
Yeah.
I see it.
Yeah.
Okay, thank you.
Yeah, being solar wind parameter at the same time just means we shifted the dipole tilt. Yeah.
I see. Thanks.
So this is somewhat the analogy that if you see here at 16 UT at uh, 10 October here, specifically we have see the dipole tilt, which is zero somewhat like, so the north pole was towards the sun, the south pole was away from the sun, and it's as storm progress, you see at 22 UT, the south pole is started coming towards sun. So if you see at specifically 22 UT, it started from here, and then almost for the 12 hour that south pole is more towards the sun. So you will see here for the next figure, it's like the south pole is more tilted, and here you observe the storm peak and the peak in a asymmetry. And here for next for the next cycle, the dipole tilt is again coming back to like it's here, it's coming back at zero, and you see the south pole here at this side, it is coming again towards the or its motion is anti-sunward. So here are the basic, or here are the both parameters for original and the UT shifted run. For the original, you see everything is there with asymmetry, and for UT shifted, you observe that this asymmetry being shifted towards 12 hours towards or 12 hours earlier when we shift the UT or the dipole tilt. There is asymmetry here in CPCP. The currents, then hemispheric power with particle precipitation, it's still the symmetric or the Joule heating due symmetric. The basic thing that we observe is the asymmetry in CPCP, which being shifted earlier. So when we here we compare the both parameter like CPCP, potential, hemispheric power. Here we compare the auroral electrojet activity. So as we know that this auroral electrojet activity, we have both eastward electrojet and the westward electrojet being they've been significant in specifically storm time. So these you see on the left side, there are the SMU and SML index. SMU stand for it's like AU and AL index. AU denotes eastward electrojet, where AL denotes westward electrojet. And when these products derived from supermag stations, it is SMU and SML. So we calculated or we plotted the synthetic SMU and SML from both of our run, where the light shade is associated with the original run, and where a dotted dark curve associated with a UT shifted run. And you observe that here the SMU, that is eastward electrojet, being enhanced in UT shifted run. So this SMU or all the electrojet activity is more controlled by the Hall current or the Hall conductivity. So here on the left side or the right side, we plotted the we showed the distributions of Hall conductivity for this for original run, and this is for the UT shifted run. So you observe that at original run during a peak or minimum C match, the North Pole and the South Poles, you see the North Pole being quite darker than the South Pole. So this means that the orientation was like this. So, and when the UT shift things are there, the North Pole and the South Pole, they are more aligned, and in the North Pole, the conductivity, Hall conductivity, if you see, it's increased. And that Hall conductivity, if you see here, the precipitate or with the field aligned current being more here concentrated than the original run. And that's the basic difference, or that's the basic cause to observe these SMU or synthetic SMU indices more or enhanced in UT shifted case. So the main thing about is like, yeah, we know that at equinox we observed like a symmetry in both patterns or at both hemisphere, but still the dipole tilt is one of the factor which can create additional asymmetry here. And this storm is specifically a such coincidence that when the South Pole or the tilt where the South Pole was just turning towards the sun, the minimum or the large step in BC occurs, which causes the storm minimum, and we observe this asymmetry and the different storm evolution. So yes, the UT matters at what time the storm hits or the magnetosphere, it matters. So whatever we did with remix, where we use specifically or like idealized dipole magnetic field, but there are different models like IGRF, where the magnetic field is no more idealistically dipole. So there you see that if you see here, there is a shift or there is a variation in particularly the poles. Like if you see in IGRF, it's a variation from 1990 to 2020. It's like here. And when we consider the eccentric dipole location or the eccentric dipole that's been simulated or that been proposed by Koshak and Fraser-Smith, you see there is a large offset here in the South Pole. So with idealized dipole, we are getting the result, but with this non-ideal dipole, the result may get changed, but the symmetry will be still there because the pole motion is still there. The one pole is going sunward, one pole is going anti-sunward, so the effect will still be there. So what will be the future prospect? Like as we know, this diurnal variation is observed near equinox where it's more, but what if the storm occurs at solstice? What if a storm occurs? This storm occurs at 20 days past to the equinox. What will be the things when the storm occurred 24 or the 12 days back or 20 days back to the equinox? So the things will be different. So the future perspective, we want to investigate what will happen at different season. We can extend, like we did a 12-hour shift, but we can extend it up to like 24-hour. We can reduce it up to 2, 10, etc. And the important fact about, like, we have that historical storms like Carrington event, Halloween storm, or May superstorm. So how the things means what will be the things, how the thing will change if we shift that storm, or what if that storm being hit by 12-hour before or 12-hour after? What will be the thing? What will be things or consequences in geospace that we are more interested? And yeah, thanks. This is all about the summary.
Thank you. Are there any questions?
Yeah, I have two quick questions. When you say we go back to supposedly dipole, right? Those are because the daytime or whatever UT difference in the conductivity, but I don't see any quiet time asymmetry if you go back. So why is that? Supposedly it could be the same, right? Although it can be minor. Yeah, but it looks like, say, the quiet time looks very similar, even the same. Only during those specific period that you say there's large difference. Why? It's supposed to be.
Sorry, means why we see this specifically at this time
and not during quiet time.
Yeah.
Okay.
The thing is here, the relation is here. Means this is quite a coincidence where the storm being maximized at a particular time where South Pole was more shifted towards things. So if you see here where the storm means this has been observed where the storm is reached towards the like 350 nanotesla, and before that where the things like more towards or there the things like, but this observed specifically where the storm reached towards that extreme and specifically being coincide with that time.
Yeah, no, sorry.
Yeah.
I know the storm and make it looks bigger, right?
Yeah.
But in the quiet time, the same conductance effects are also there.
Yeah,
But I don't see maybe it's too small or the.
yeah, maybe it's too small specifically, or I can say here.
So the hemisphere power look almost the same or geohelium, which is a little bit surprising to me. As quiet time should also have something.
Yeah,
there.
they should have something, but
Yeah.
as the conductivity increases and when in a storm time,
Oh yeah.
the conductivity increases, that reduces the potential. So as order of conductivity increase in either hemisphere, it reduces the specific potentials associated with the storm time. That's
I think the coincidence, if you go back to the plot where you show the shift,
Yeah.
the coincidence, so we're on the left-hand side where you see the dipole tilt plot second down being close to zero.
Yeah.
Sideways. That tends to make north and south more symmetric.
Oh, yeah.
Which are how it's tilted. And that just happens to coincide.
By coincidence.
It's
Okay.
quite agrees.
Okay.
So I don't think I think that's the main reason.
Okay.
So that suggests that you could do a simulation where you had no dipole tilt at
Yeah.
quiet times.
Yeah.
Yeah.
Okay.
I mean, boring, but they should look the same.
Then another
I think there's significant.
question is, you say geohelium and others asymmetry, but most of the asymmetry should happen in daytime, right? Because your conductance differs.
Yeah.
But nighttime should not have much
Yeah.
asymmetry. That's right or not?
Yeah.
Have you looked at that? You feel like current, Duke heating pattern on those things should be mostly controlled by daytime.
Daytime. Yeah.
That's right.
Yeah.
So
Daytime.
nighttime should be roughly the same. Or,
Night
you have a huge
depends on the nighttime activities specifically that being dominated by other like magnetospheric
Yeah.
activities. Yeah. So the difference might be there, but it might be associated with that activities, not strongly associated with this.
Okay. That's
you
right.
do a UT shift run using GTR?
It's
Because-
quite difficult. Means we need to flip the whole Earth towards it. Like so, I didn't did that. Yeah.
You can move solar wind by 12 hours.
Oh yeah. That.
Okay.
Yeah.
But it-
All the inertias.
Oh, yeah. Okay, good, nice.
That's Dom.
Right. Okay. Yeah. Let's talk, Kapesh. I noticed in that time series of your dipole tilt, the value itself is the minimum is like a minus 15 degrees. So that's also when the asymmetry is the strongest. If you go to that, yeah, like here.
Yeah.
So basically, like when your tilt is the negative largest, you expect the largest symmetry. I know the maximum value here is slightly above 0. That's certainly determined by the actual two axes. So what if in a imaginary experiment, the dipole tilt goes to a maximum of positive 15? Do you expect in that case the southern hemisphere would show a stronger CPCP?
Sorry, can you please repeat?
Basically, like if you do just like an idealized experiment, when the dipole tilt angle flip the sign, so let's say now the maximum is positive 15.
Yeah.
Right, and do you expect like the southern hemisphere would show a larger CPCP than the northern hemisphere?
It will depend. Either means it depends on which hemisphere is getting more conductivity, the conductance, it will reduce the potential, where the less means it's vice versa. As pole move towards the sunward, conductivity will increase, the CPCP will decrease, and it moved out or anti-sunward, the things will be vice versa.
Okay, well, just to think about that, like for imaginary planet somewhere else.
Or we can means if these things is happening at like equinox at September, if the things happens at equinox at March, the scenario that like it will like a plus 15 degree will be there, and that where we can observe the shift like in the CPCP will be more in the south pole than the north pole.
Okay, thank you.
So the paper is under review or submitted?
Yeah.
Okay.
Question for me. So you focus on your high latitude asymmetry.
Yeah.
Did you look at all at any other effects of the fact that they're sort of asymmetric?
I'm
Or
interested in like seeing the fact like the neutral density in the thermosphere and other kind of things, but the current focus is only on the high latitude rather than the.
So use GR, you cannot look at the thermosphere.
Okay.
You have to be GTR, so have a thermosphere.
Nice question. So in one of your computer simulation, I think you changed the by value so to a constant, whereas in some simulation you change to the upside, just flip the sign.
Yeah.
So you didn't see always change of the symmetry, right?
Yeah.
So I wonder, could BY gonna change the magnetic reconnection efficiency between the dawn and dusk side. I wonder how well the Gamera model can resolve this.
Means if you see here,
Mhm.
we cannot say that it is exactly same as the previous run. Some modulation is there, which is associated with that BY, and that's why we are observing like some differences here. But the fact that this asymmetry was being dominated by that dipole tilt, and that's why we were not able to depict it when its BY is our neglecting effect of BY. So probably the things will be there, but as the main influence of this asymmetry was related to dipole tilt, that's why I think we are not observed the changes due to BY. But the observation is we observed some kind of change, some modulation is still there, which is associated with BY. This means that Gamera is handling kind of things.
Mhm. So I guess my question is how the Gamera model, they have the procedure to reading different BY and then mapping all the facts down to the ionosphere. I'm not sure Gamera can do that.
Yeah.
Yeah. Hmm.
Thanks who map BY simulator. Yeah. Yeah.
Mhm. So using like a flat BY, you're gonna see different change of the convection patterns.
Yeah. Yeah. You have that.
Yeah.
So far the coupling between the magnetosphere and ionosphere is just the conductance.
That we observe with the associated with the dipole tilt.
Mhm. Thank you.
A lot of other things.
Lot of other things.
There was another student here, Josh Wong, who some of you may remember, who was looking specifically at time FPY conditions at BY and BZ, looking at alphanic point fluxes generated by flux transfer events on the magnetosphere. It's very closely associated with the BY effect. But he did not look at asymmetry, hemispheric asymmetry. That would be an interesting thing to look at.
Any other questions? If not, so thank you again.
This is